All right. Oh. All right. Let me start a little bit from the beginning again. Oops. Okay. So if I've got, it'll get here in a second. A is n by n. And let's say it's got rank n. So it's got full rank. What do we know? We know that A is invertible. Oh, I'm sorry. Oh, you didn't turn on. Hello? Hello? Oh, good. Okay. Sorry, guys. It was saying on here, but apparently these guys didn't want to wake up yet. Oh, let me do this too. Turn this guy out. Decrease the glare. Just a bit. Okay. Okay. So real quick, anytime we're going through this list right now, any damn time I'm saying anything spewing from my mouth, and I say something that doesn't make sense, stop it. Just stop me right there. Say, hey, just one. You go over what you just said. What the hell? Why? Why is that true? Yes? The minute I say something, it's not your responsibility to keep us on pace, it's mine. So if I don't have time, I'll tell you, see me after class or whatever. Are we cool so far? Ignoring my fantastic writing, I have an n by n matrix and it's full rank. That means every single column in it is independent, which means it's invertible. Is that cool? I like it. What else? Anybody else have anything else? I think somebody said null space is what? Zero. Null space is the zero vector. Why? We just said it earlier. Sorry. The only way to get zero is if everything is zero, yes. If I use a zero vector is the only way to make AX equal zero. Because why is a null space more than just the zero vector for a non-invertible A? If my A is not invertible, what does that mean? Don't tell me, that means you can't find an inverse. Yes, I know. If I have a non-invertible A, what does it tell me about the columns in it? They're not all, which means some columns are multiples of others, yes, or combinations of others. Therefore, I could use that to create a zero answer with non-zero vectors. Because if column 2 is twice column 1, then I can just make my vector be 2, -1, 0, 0, 0, 0, and then I'm guaranteed to get a zero answer. Let me say that again. If column 2 is twice column 1, you with me? Then wouldn't twice column 1 minus column 2 with zeros everywhere else, wouldn't that make 0? You with me? Let me write this. If A not full rank, let's say A has rank R, then AX equals 0 has more than one answer, well, has an infinite number of answers. Because if, for example, I get my R0, and it's this. What did I just say? I forgot. You can do it, Jeff. Yes, I think it was this. Yes? Let's say I row reduce and I get that much. It doesn't matter what else I get. You with me? Wouldn't I, if X was -2, 1, with nothing but zeros afterwards, does everybody agree that that vector, when I multiply it by the original matrix, will come out to be 0? Because the second column is twice the first, therefore -2 times the first plus the second one will cancel. I'll end up with the same numbers, different signs. Does everybody get that? That is why, if I have any dependent columns, does it make sense what I'm about to say? I can take advantage of their relationship to find vectors that will make the result 0. Okay, cool. Coming back. Therefore, if none of the columns are dependent on any of the other columns, I have nothing to take advantage of. The only way I can get a zero vector is to zero everybody out. How do I create the column space? What do I do in general for any given matrix? How do I create the column space? No, that's how I find the basis vectors. So say I did all that, I get a bunch of basis vectors. How do I create the column space? What do the basis vectors do? What do the basis vectors do for the column space? What do they do? The basis vectors do for any vector space? Sure, I get them from the independent columns. How do I construct the whole space from them? Is my question. Yes, all the linear combinations. Cool. Let me stop for a minute. If I have two linearly independent columns, when I combine them, I get a plane. Geometrically, that represents all the vectors that those two columns could create. Does that sound familiar? We talked like that before. Okay, I like it. Is that okay? So the null space, if I have an invertible square matrix, the null space is 0. The minute that, now there's more to this list, but this is all I wanted for right now. The minute that I have something that's not full rank, let me give myself some more space. The minute I have something that's not full rank, then the null space steals some of that dimensionality. I don't know if you like this way of saying it. So if I have an invertible matrix, it's a full rank, yes? The column and the row space get the whole thing. And what's left over for the null space? 1 point. We left a point for you, yes? Okay, I like it. The minute that I have something that's not a full rank, however many columns are not independent, those go into the size of the null space. And you guys know this. If my rank is R, then what's the rank of the null space? Yes, and that, what you just said is, full rank would be N. I lost R of those, right? So that all of that goes into the null space. The leftover goes into the null space, yes? So if I have R in my column space and my row space, because those are the same size, then the N minus R must have gone into the null space. Funky. And again, why does that make sense? Because as I lose independent columns, those must be dependent, giving me more ways to make 0. Does that make sense what I just said? Sort of? Okay. So, one way you can look at this is the rank of the null space plus the rank of the column or row space has to equal the full rank. Yes? Is that cool? Yeah. So, on the, does that make sense for the quiz? I think that was the quiz question you're asking about.
Yeah, he was asking like what do they add up to, so yeah.
Yeah, so then you should, when you add them, you should see that the answer should make sense according to what was going on with the matrix. Is that cool? Did anybody get that, you think? You don't have to tell them. Okay. So you just tell them. All right. Anything else from the quiz? Well, it's still yet. I'm sorry, Joe, I'll come back. Go ahead.
So for number 3, where it says that y is a vector b1, b2, b3, not subspace of R2, then b1 times b3 is
Yeah. Okay. Okay. Does everybody remember that problem? So many guys that said B1, B2, so many guys that said B2, B3, so many guys that said B1, B3. Didn't matter. So let's say, here, to give you an example, I'll give you one nobody had. Because what was it? It was, where'd it go? Oh, okay. So I'm going to talk about R4. And I'm going to say I have a bunch of vectors that where, oh shit, B1 times B3 times B4 must be 0 in order for it to be in this subset. You guys with me? So a potential subspace, we'll call it a subset. Does that make sense? It's definitely a subset. Okay, so a plane that does not go through the origin, is that a subspace?
No.
Why not? It doesn't contain the zero vector, yes? But is it a subset of R3, whatever the total, right? If I have a plane in R3, is it a subset? Of course it is, because a subset is just a collection of things from that space, and that's definitely what a plane is. Does that make sense? Okay. So I don't know if this is a valid subspace yet, right? Does it contain the zero vector? Oh, hell yeah. Yes? In fact, the zero vector is the easiest way to meet the requirement, yes? So to be in this subset, when you multiply all those together, the one B1, B3, B4, you better get 0. Yes? Okay. Can you, somebody give me one example of a vector in the space? 1, 0, 2, 3, no, come on. There we go, that's in the space, right? B1 times B3 times B4 is 0, yes? Okay. What about 1, 0, 0, 2?
Yes.
Yes, right? Now, the minute I do this, I'm going to give the whole game away. Not only, what are the two most important things? There are other things that vector spaces happen to do based on how I kind of define operations, but what are the two most fundamental things a vector space must follow?
Closure for addition.
So it's got to be closed under addition, scalar multiplication, and it has to have the zero vector, correct? You guys with me? Okay. So does this have the zero vector? Yes. Is it closed? What do I get when I add the two vectors I've got up there? What do I get when I add those? I get 1, 0, 2, 2. What's B1 times B2? I'm sorry, B1 times B3 times B4? 4. Which is not 0. So when I add two vectors together, is it still in the subset? No. So is that a subspace? No. It's a subset. It's a collection of vectors that are in the space, but it doesn't get to be called a subspace. Do you guys see that? Do you guys get that? Okay. So to be a subspace, every element in there, when I operate it with some other element, they got to stay in that. They got to stay in that subspace. That's why it's kind of silly. If I give you two vectors, say I give you the vectors 1, 2, 3, and 3, 1, 4. Are those independent then?
Yeah.
Yes. They're no. What dimension of space do they span? Careful. Don't say R2, because that's a specific subspace. That's the plane XY and the XYZ space. You guys kind of with me? We talked about that before, so I can't say that because I don't know that for sure. Let me see. Let's see if you guys are with me. This is easier. I've given you two vectors. You give me any number of independent vectors. When you take all the linear combinations, it must be a subspace they create. You guys understand that? Because the zero vector in the subspace that creates. You can do it. Because what is the subspace they create? These are the basis vectors, yes? This is the basis set. How do I write an expression for every vector these create? How do I write an expression for anything in their space? Yeah, so C times this plus D times that, or whatever letters you like. You can use X1, X2 if you're boring like the book. That's okay. Right? So is 0, 0, 0? Is that vector in there? Yeah, if I make C and D 0. Yeah. So it's kind of, I want you to see, if I give you a basis set of vectors, they automatically span a subspace. Or a vector space, I should say, because they might say, if I gave you 3, that would actually span the entire R cubed, yes? You guys with me? Does everybody really understand why I cannot say that those span R squared? Now, maybe they do. Does anyone know how to check if they do? Do you all agree there's more than these spaces? Or let's call the vector space that these span, I'm going to call the space, let's call the space V squared for a square vector space. You guys with me? Okay. Does that sound okay? I can call it whatever the hell I want. are there other vectors that are also bases for v squared? Let me give you another two. 3, 1, 4 and 2, 4, 6. Are those basis vectors? Yes. What about 1, 2, 3 and 4, 3, 7? Yes, because I'm just adding these together, yes? Any combination or multiple of either one of those that remains independent from the other one you pick are also basis vectors. Does that make sense? It's the same thing I said earlier. I think I was doing this with you guys. Wasn't it you guys in my other class? I was 281 and 284. They overlap so much. Here's my 1, 0 and my 0, 1. And then I can make every vector everywhere with these, yes? If I can also make every vector everywhere for these too, yeah? You guys follow? So I don't have to have the perfect things to have a basis for my space. If my space is the xy plane, these are a basis, these are a basis, these are a basis, this is not a basis, this is not a basis, this is a basis. Okay. It has to have a component. Now this is going to feed into chapter 4 we're going to get to someday. It has to have a component. Do you guys see the idea? What's true about two vectors that want to span R squared? They have to have a component. One has to have a component that is perpendicular to the other. Because what's the only way that I can have two vectors that don't span R squared? Is if they are multiples of each other. In which case, do they have any component that's perpendicular to the other one? No. You guys with me? So in chapter 4, we start talking about orthogonality, which is another name for perpendicular. Perpendicularness, we call it orthogonality. They both sound made up, but the second one is actually a real word. Perpendicular, what did I say? Perpendicularness? Sure. Okay. So, real quick, does anyone see a way to get a better set of basis vectors for this space? Do you all agree that 1, 2, 3, and 3, 1, 4, they're fine. They don't have any negatives, but they kind of suck. Why do they kind of suck? Neither one has any zeros, for example, right? That would be great if some of them had zeros, yes? Anybody have any suggestion as to how to kind of reduce this down so I can see a more fundamental set of bases? Yeah. So again, what did I just say? If I take this plus or minus any multiple of this, isn't that new thing still a basis vector? Because it would be independent from this. Because these two are independent, I'm using a multiple of this to create new ones. Therefore, the new thing is going to be independent as long as it's not a zero of that one. Okay. So if I could actually put them in, if I wrote them correctly, and just row reduce, yeah? Which would accomplish exactly what you're saying, correct? You're saying take 3 times 1, 2, 3, subtract it from 3, 1, 4. I think that's what you're saying. All right. What I'm doing right now, do you see how this feeds into everything we've been doing? Yes? This whole discussion we're having right now feeds into everything we've been doing. So, real quick, when we get CR, when I say CR, what do you guys think of? Say it? Yeah, it's like the column times the rows, yes? The columns and the rows that kind of come together to make A. It's the first, I think that is the first factorization we did. Okay. Aren't the rows in R that aren't zeros, aren't they basis vectors for the row space? Okay. And I get the columns from the original one based on where the pivots are, where the ones are, the leading ones. Okay. So obviously if I row reduce this, I'm doing that R0 kind of work. And I think you all would agree that if I had 1, 0, 0 and 0, 0, 1, those bases kick ass. Because then if I said construct 5, 0, negative 7, you don't have to think about it at all. Yes? But if I gave you 3, 0, negative 14, and negative 7, 0, 11, and I said now construct 5, 0, 7, whatever the hell, that would suck. Do you all agree, though, that I could construct 507 out of those? Yes? How do you know? Yeah, how do you know they're independent? There's only two of them, so of course one is not a multiple of the other one, so they're independent, so they must span the same thing. So these two. What does this span, by the way? Can anybody tell what that spans? Tell me a plane. Okay, this is XZ plane. And of course this also spans the XZ plane. Yes? Okay. So how many possible sets of basis vectors are there for any given space? Infinite. Some of them are kind of dumb. 3, 0, 0, 4, 0, 0. Yeah, okay. And then you start getting the combinations, yes? Okay. All right, I'm sorry. I went way off on somebody's question. I went way afield. I'm sorry. I can't remember if I even finished what I was talking about earlier. Anything else from the quiz? I think that's what I'm on, right? The quiz? Is that what I'm doing? I love you guys. You're guys. Oh, man. I'm tired. Anything else from the quiz? Okay. So what I want to do today, real quick, with the little bit of time I have left, is talk. I wanted to do one quick example. Let's see if this can be quick. Just to make sure everybody's cool with what we've done most recently. So if I give you this matrix, and this vector, and I ask you to tell me what's the dimensions of all the subspaces we talked about? Can somebody pick one subspace and tell me how to work something out so I can get the dimensionality?
Null space.
Say again?
Null space.
Null space, okay. This guy will come in handy in a minute, but right now we're just talking about this guy. So how do I find out the dimensionality of the null space? Huh? Row reduce. Now, real quick, when you see a problem like this, do you remember this from the practice we did last time? I gave you that vector b, so what do you think we're going to eventually ask you about? Complete solution, kick ass, yes? So I might as well augment that. Whatever work I'm going to do with that will not be affected by putting the b in there, yes? We can just kind of do it. That's what I was telling you guys. So don't redouble your efforts. Redouble, is that right? Who knows? All right, so this is not very difficult to do by hand. Maybe on this next test I'll actually give you one you can do on the calculator. We'll see. And let's keep track of what we're doing. So real quick, I could take row 2 minus row 1. Is that cool? And that would give me, and put it in row 2. So that would give me 1, 0, 3, negative 1. This would be 0, 1, 4, 3. Is that cool so far? I'm tired. Who knows? And then, what else do I want to do? How do I kill the 4? Row 3 minus 4 row 1s. Put the answer in row 3. 0, 2, 8, 6. Yes, okay. And then, of course, what do you guys notice? What do you notice, sorry? Yeah, so if I take 2 row 2 minus row 3, I'll get a row of zeros, yes? And then I've got my 0, 1, 4, 3. And my 1, 0, 3, negative 1. Anything else I can do? Or that I want even to do? Can you guys see your leading ones? Okay, so I can get a lot of shit from this, yes? From what we've done. What have we done? Is B in the column space of A? Let me give you a question. I haven't really asked you that directly. Is B in the column space of A? What tells you that? Yeah. What would have to happen for B to not be in the column space of A? This would have to be something other than 0. Yes? You guys with me? Is that cool? Okay. In order for B to not be in the column space of A, that last dude here would have to not be a 0. Does that make sense? Yes. For B to not be in the column space of A, that last entry would have to be not a 0. What does that mean equation-wise? 0 equals number. And that can't happen, yes? Okay. Everybody with me? So that tells me Hash Jeff picked a good B. I wasn't really sure. I was hoping Hash Jeff wasn't too movie when he picked that. Can anybody tell me how to get the null space? That's what we're currently working on. How do I get the null space? Yeah, x1 plus 3x3 equals negative 1?
X2 plus 4x3.
Equals 3. I like it. I'm sorry. Null space. Null space. This doesn't really mean anything right now. What should it equal?
0.
0. Thank you. Null space should be 0. Okay. That's the one drawback about doing that. You have to remember you did that just for later. I haven't talked about AX equals B yet. So null space is when B is zeros. Yes? Okay. So then what's my free variable? X3. And that, of course, makes sense because it comes from the only column that was dependent. Yes? So if I call X3 T, what is X1? Negative 3T. And what's X2? Negative 4T. Kick ass. And of course, I can write this as negative 3, negative 4, 1 times T. So my basis vector for my null space is negative 3, negative 4, 1. That is a basis. So my null space is basically along that line. That is a line in R3, yes? But it's just a line. It just has to be in a bigger dimension. So instead of being on this plane, it's just coming out of the plane. It's just still a line. Are you guys with me? So how many dimensions does that not account for? And that makes sense because what's my column rank? 2. In fact, my rank for A is 2, yes? My column rank is 2, my row rank is 2, also 2, because I can see my R0. What would R be? Be really careful. What's R? That. Yes? That's R. Okay, I like it. I like it. Now, if I ask you, what's the complete solution to AX equals B? What would you tell me? Now here's where I could go back. Here's where I could have been smart. I could have done this and got the whole thing at once. But, we'll get over that. If I make that negative 1 and 3, I'm not sure if you guys can see. It's not going to do much to me. So this x1 would have been negative 3t minus 1. So then this would have been negative 1, and then this would have been negative 4t plus 3, so this would have been plus 3, and this would have been 0. Okay, so the complete solution to this would be negative 3, negative 4, 1, t plus negative 1, 3, 0. What's my column basis vectors? My column space basis vectors. Why can you see them really easily? Yeah, because I can see my leading ones. So 1, 1, 4, 0, 1, 2. Yes? And that's got rank 2 like we wanted it. We needed it to because the null space had rank 1. Okay, that kind of very quickly is a problem like we did last time. Okay. So what time is it? All right. I love the timing. Oh, this class drives me crazy. Okay, we're getting it through. Very quickly, I asked you guys last time to read it 3.4. There isn't a lot of new stuff in 3.4. 3.5 does throw something a little new at us, but it's related to a problem I asked you about before. All right, I did this on the chapter 3 practice, specifically because I knew this was coming. But do you see how I can get the column space from the original columns? But where's my row basis vectors? Where are my row space basis vectors? What are my row space basis vectors? Yes, it would be 103 and 014, yes? If I wanted to get my row space basis vectors from my original matrix, I'd have to transpose A, and then row reduce it. Because if I transpose A and I find the column space for A transpose, yes? The column space for A transpose is what space for A? The row space. Now, real quick, it's kind of a silly thing. It seems silly right now, but to make a complete picture, I want to be able to talk about all the possible subspaces that I can see from this matrix. The row space for A, we already got it from R. But if you're like, well, what would it be from the original row vectors? What if I wanted to know what the basis vectors were from the original row vector? We can do that from the column space, can't we? Then I would take A transpose and get the column space. Because the column space for A transpose is the row space for A. Okay. Now, we did something earlier. I don't know. Do you guys see the idea? I did kind of like a reduced row space basis vectors, but a non-reduced column space basis vectors. Does that make any sense what I just said? Would you all agree that these vectors are reduced? Okay. Yes? Yes? You concur? Okay. And these vectors are not reduced. So how can I get a reduced set of basis vectors for my column space? We talked about it, actually, this is weird, just a minute ago. If I just transpose my column vectors, row reduce, bam. So that makes a complete picture. When I get R, I get reduced basis vectors for my row space. Kind of like the better version, the ones that have some zeros in them, yes? So I can at least tell which planes are kind of like existing on, okay. My column vectors, they sort of, currently, so far, we've had to get them from the original. So they weren't like the best around, okay. But if I transpose the two vectors in my column space and row reduce, I can do something the same as I did for my row space. I don't know if you guys are listening. So if you need the best building blocks for your column space, you transpose the vectors you got so far and row reduce. That's exactly what we did in row space. Okay. Let me see. 3-4 really though, 3-4 is pretty much a review. If you read through 3-4, it's kind of like Strang is catching up with all the conversations we've had. I have no idea if anybody actually did that, but if you did, I don't know if you agree with me. I'm trying to remember if there's anything different in here, a little bit. Let me ask you this real quick. Are these two vectors independent from each other? Why not? So let me call this one V1 and I'll call this one V2. Now, be very specific. Why are they not independent?
V1 equals 3 V2. Or V2 equals 3 V1.
All right, I was excited there for a second. V2 equals 3 V1, but can't I say that a different way? V1 equals 1/3 V2. Yes, okay, right? You guys with me? That's kind of silly, but there's no damn reason in the universe that I can't say 3 is my basis vector, damn it. Right? And V1 is dependent on that dude. Yes, poor little 3, we keep calling him dependent. He could be the independent one. Why not? Because that seems silly. I know. Purposefully I'm saying that kind of shit because it is silly. Now, real quick, are these two independent? You can do it. You can get there.
No,
You can get there. Why?
because V1
Yes, yes.
0 times.
Yes.
this.
So V1, if I call this V1 and V2 again, yes? V1, 0 V1 is V2. Is that cool? Now, can you turn that around like we did just a second ago? Okay. So in that case, in this case, which one is the dependent vector? This one, because it depends on V1. I can't turn that around because 1 divided by 0 is, or not even infinity, it's just, I don't know. Okay. That's a little side note I just want to point out. So every time I say 1, 0, 0, 2, 0, 0, oh, so the first column is independent. That's a little arbitrary. It's understandable. Of course, I'm going to pick the one that's not a multiple, but the second one is 1/2 the first one. That's also a multiple. Okay. That is one little thing that I thought was sort of new in here. Not really new, but let me ask you this real quick. If m is less than n, think about that for a second. What does that mean directly? What is m? The number of rows. And what's n? Columns. So if you have less rows than columns, what must be true? Sure. So if you have less rows and columns, so something like 1, 2, 3, 4, 5, 6, 7, 1.
It's more unknowns than the equations.
Say again?
There's more unknowns than the equations.
Okay, good. More unknowns than equation, so it's over or under? It's determined.
Under.
Underdetermined. How many total independent columns are there? In the example I gave. 2, right? So if m is less than n, it's undetermined, I'm guaranteed to have at least one dependent column vector, yes? And again, this is something we sort of talked about before. Guaranteed, how do you spell that? At least one dependent column vector. Just depending on how freaking big n gets, yes? Okay. All right. I see you guys. I'll stop. I'll shut up. All right, guys. So here's the plan for Wednesday. We're definitely going to finish up chapter 3 Wednesday. We're going to get into chapter 4. More than likely, we're not going to finish 4, which kind of makes sense because the first test we pushed back, and then I had to finish 2-4. So that kind of only makes 2-4 will be on the next test. Yes. Okay. And we'll see how much more homework I can create. I'm trying. All right, I'll see you guys Wednesday. The quiz graded, all that kind of stuff. Thanks, man. Don't forget your ID.
Because it doesn't show a line, because it goes through zero, and then the plane is also goes through 0.
Sure.
Could you make P like a part of the line?
That's what they're asking, right? So it's either the line is on the plane, right? In which case the smallest vector space containing both P and L is something or something.
And I was trying to write it like that, would that be fine?
V equals dp,
Like,
d element of r.
D is what is it?
Oh.
A scalar, and then P is your plane, and the plane is the makeup of the line, and the concept goes.
I see. Okay, so here's the thing. What are the two possible situations? The line is on the plane, and if the line is not on the plane,
Then I can't pass 0, 0.
no.
Oh.
So let's say this is 0, 0, right? And doesn't this line go through 0, 0?
Yes.
So if the tip of my finger is 0, 0, 0, yes? Does the line still go through 0, 0, 0?
Yeah.
Yep. But how big of a space do they span then? Plane, line,
Would be
all of our cube. Do you see what I mean? So you got the kind of the right idea. If it is this, then it would be a combination of the vectors that are in the plane. Yes? Does it make sense? Because this doesn't add anything new then. Yes? That's the idea. Does this add anything new if it lies in the plane? No. The minute it's not in the plane, it adds something new. There's a perpendicular piece to it
Yeah,
that lets me get out of the plane. Now I can fill all of the parts.
but then what would be the smallest combination at that point? Would it be? 'Cause it
Well, the
says-
minute the line is not in the plane, it's got to be all of it. What is the smallest is if the line is in the plane. Yes.
So, okay, so it's a combination of that, okay.
I was just hoping to look at your notes. I didn't really get where you were getting the stuff from null space.
Null space.
Yeah,
Oh, here.
This, okay. Because you were picking up like -3t, -4t, 1, and then, but you circled that, but these aren't from that.
What do you mean? So the null space is when this is equal to 0.
Mm-hmm.
So it has nothing to do with this.
Yeah,
It's
just
that
you circled
equal to
them.
0. Yes. Well, I circled it as I was talking about something else. Yeah. So I might have been talking about adding this on because that's the answer we got from row reducing. Yes? And that's why that's the particular solution.
So then this is just in terms of x1, that is?
What do you mean? Sorry.
This stuff?
Yeah, this is setting this equal to 0.
Mm-hmm.
So then I subtract that, I call x3t.
Mm-hmm.
So the next one will be -3t, and x2 will be -4t.
And then where did you get the t for the third one?
Oh, I had to call x3 something, because again, I could give
Oh,
x3
yes.
a number, but instead I give it a t, because I could give it any number I want to. And
Yeah.
whatever x3 is, I can then determine the other two.
And then this is just the b vector?
That is the vector that when I operate on it with a, it creates b.
Okay.
Yep. So it was a little quick because I wanted to try to get a little bit of 3-4 talked about, but it's basically what we did on that last sheet together.
So it's basically taking the null space you got and then converting it back into terms of A.
Converting it back into
Or-
terms of a.
Converting it into terms of B?
So if I want the null space just by itself, that is when this equals 0, 0, 0.
Mhm.
Yes? And I could do that very easily by just putting zeros here. Then I can focus on the null space. Then I can see what my free variable is. Because x1 depends on x3 and x2 depends on x3. So x3 is the free variable.
Okay.
And I can tell where the free variable is because it comes from the column or columns that are dependent. Yes? So this comes from this here doesn't give a shit about this guy.
Mhm.
It's just what makes that matrix the 0 vector.
Yeah.
Right? Okay.
So then this comes in to do. 'Cause
That
this
is
null
the
space.
yeah, that makes it 0.
Yeah, that's the null
And if I
space.
add the vector that makes it become this, then I'll get this.
Okay, yeah, this one was, okay.
So if I do, watch this. This is kind of cool. This is something I haven't shown people
So
yet.
it's just a complicated way to get B?
What do you mean? No. B is given to me. Get
Well,
it?
then why do you want that?
Because that's the vector that when I multiply a by it, I get b.
Yeah, but you already have. Oh, is that?
No.
So
Come
that's
on.
X.
I'm trying to solve. Yes. Good old algebra.
So that's
Yes.
X. That's what you wanted.
That's
in
X.
first.
Yes.
Okay.
So if I operate on this vector, any combination, any multiple of that vector, plus this vector, this times this gives me 0, and this times this gives me -1, 2, 2. Yes.
Okay, so you're multiplying A into null space and
Yes. So
The
the
X
complete
vector.
solution to this is null space vector, or a combination of vectors, and particular vector. Because A times these give me 0, and then A times this gives me this vector.
then why construct it that way? Why not just use LU?
Oh, LU is one way to get to a method to have a computer really quickly do these. Yes? What we're doing right now is focusing. LU doesn't, well, when I row reduce, I get U. L, of course, comes from other considerations. Yes?
Yeah.
There's
I
a few
remember
different ways
that.
to do it. So what's kind of funny is when I row reduce, that helps me figure out what the null space is. Row reducing, you could also see it as helping you figure out what U is. So at that point, you can go off two different ways. You can either do the LU approach to solving, or you can do what we just did for solving.
Just seems quicker to do to figure out what L is, because U is super simple.
Yeah.
It's just because that's just upper triangular form, and then you already have E, so putting E in terms of inverse E is really easy.
Well, was this difficult?
It took longer.
I don't know about that, to be honest. Bam, bam, bam. But I do agree with you. If I'm talking about computer program and my only concern is solving AX equals B, yes. But this shows me null space, it shows me column space, it shows me row space. This is more what I use for that specifically. With that said, row reducing also gives me U, so it kind of feeds into that. So that's why at that point I can go one of two ways. Does that make sense?
Maybe I'll read the textbook later. That's where I'm getting most